Welcome in part one of radiation effect on CMOS imager. I'm Jérôme Pratlong, Chief Engineer at Teledyne E2V, specialized in visible and infrared detectors for space application. There are three types of radiation testing for imager. One is total ionization dose. The second one is total non-ionization dose, also known as displacement damage dose, and single event effect. In this part one, we will focus on total ionization dose. In the part two, in the displacement damage dose, and part three, the single event effect. The total ionization dose affects the radiometric performance of the detector, and therefore define the end-of-life condition and ultimately the lifetime. In this video, we will look at the basic mechanism of ionization, the main impact on imager, and we will share some takeaway from silicon results from Teledyne E2V detectors. The incoming photon interacts with the material and creates electron-hole pairs by a phenomenon called Compton scattering. The total energy deposited by this incident particle is also known as the total ionization dose. The main effects on semiconductors are increase in leakage and transistor noise, but it can also affect potentials and threshold. The test has to be biased. Usually the source is gamma ray cobalt 60, since it's the more realistic or representing better the reality. There are two units used, the gray and the rad silicon. This is the one I will use throughout this presentation. This type of radiation affects only the pixel. This is a representation of a 5T structure widely used in space imaging. 40 pixel is also used in space imaging and differs from this structure only by this fifth transistor here. This fifth transistor is important to enable electronic global shutter, but also is used as anti-blooming for some applications. This is a cross-section showing the pin photodiode in the middle here, made of PNP sandwich implants, a transfer gate that enables the charge to be transferred to the sense node. The photodiode accumulates the charge in electrons. At the end of the integration, the transfer pulse is open and the potential are lowered and enable the electron to go to the sense node, where they are converted into a voltage that then is read out via the in-pixel source follower here. The fifth transistor that can act as a global shutter function, but also as an anti-blooming, will have a applied DC voltage on the gate. By modulating this voltage, we can create a path for overflow, making sure that extra charge captured by the photodiode are not spilled out in the neighbor pixels. Therefore, the ionization will create additional leak path, dark current, dark signal non-uniformity, but also will increase the noise floor by increasing the noise of the in-pixel source follower. We will see also that the two other consequences, potentials and threshold shift, can be mitigated by design. The general mechanism is that the radiation interacting with a gate dielectric release hydrogen atom. This hydrogen atom diffuse into the silicon-silicon oxide interface and basically reverse the annealing effect and create path for electron to move in the structure and go to a ground potential. As I mentioned, the threshold shift exists, or potential shift. This is proportional to the square root of the oxide thickness. And with new technologies where the thickness is small, this problem is relatively low, reduced, and therefore can be handled by good design practice. Therefore, what remains is dark current, DSNU, from the photodiode, and also noise from the damage created at silicon-silicon oxide interface, damage that we also call dangling bond. In terms of leakage, there are three potential paths on this sort of pixels. The first path is below or via the transfer and global reset gates. The second path is via the trap created in the STI structure. And the third one is via the silicon surface at photodiode level. This is a table describing the different detectors we used for this presentation. We can see that there is a large variety of pixels, 40, 50, but also a variety in terms of pixel pitch from 7 micron square to 100 micron square, different QSAT of full well capacity from 18 kiloelectron to 1 mega electron, front side and back side, with and without anti-blooming, and also different type of material, high resistivity or low resistivity, that affect the depth of the depletion. This is a table of the results. We are going to go in more detail in the next slide, but from this slide, the takeaways are that lag, linearity, full well capacity are not impacted by total ionization dose, and that the threshold shift is, as expected, small, to minus 0.2 millivolt per kilorad, which means that if we had an environment at 50 kilorad, the shift will be only 10 millivolt, which is easily mitigable via design practice, good practice. Therefore, what we are left with is the impact on dark current and noise. Here is a graphical representation of the same number of the previous table that shows no really obvious trend between pixel size, full well capacity, or pixel type, which also means that between a 40 or 50 type transistor, there is no drawback of having a fifth transistor. This is representing the increase or rate of increase in dark current post-radiation. Obviously, bigger is the pixel, bigger is the dark current pre-radiation and post-radiation. But here we show that the rate of increase post-radiation has no obvious trend following pixel size, full well capacity, and pixel type. For the noise, we can observe a similar pattern, except for the case of the 40 CIS 115 here mentioned. And we can see that it stands out from the others. And the difference in terms of design of a source follower is that this pixel has a larger source follower. Therefore, in terms of noise, it's clear that the size of the pixel source followers has an incidence, and therefore that must be considered during the design. We also did a post-annealing test with temperature on the CIS 113 detector, and we can see a significant recovery post-annealing. Obviously, it's only on one detector, and we will need more data to do a proper synthesis. And we can see, as expected, that the dark current pre and post radiation are better controlled under control with temperature. As takeaway, the TID affects mainly dark current, DSNU, and noise. Dark current rate we observed are between 0.2 and 0.5 picoamp per centimeter square per kilorad. DSNU between 0.05 and 0.12 picoamp centimeter square kilorad. And the noise rate is between 0.3 and 0.6% per kilorad. From dark current, there is no strong trend across various pixel design or starting material. For noise, however, we see that the in-pixel source follower size matter, and low temperature operation enable a reduced rate for dark current and DSNU. Although we observe a change in potential, that can be largely mitigated by design, including within the photodiode, by making sure that the fuel capacity of the photodiode is bigger than the fuel capacity of the sense node. Ionization could also create RTS effects, but this is negligible and largely dominated normally by the RTS produced by the total non-ionization dose, also known as proton radiation. And this is the second part of this webinars, where we will be talking about this total non-ionization dose. We will look at the mechanism, the main impact, including RTS, and we will show and share some takeaway from silicon results from Teledyne E2V detectors.